Hello everyone and welcome to our second online lecture. This one will be on igneous rocks. I'm going to divide the rocks up into two parts. Um, Today will be igneous and tomorrow will be sedimentary and metamorphic. So rocks are really kind of the bread and butter of geology. But most geologists, aren't interested in rocks really just for the sake of rocks. We're interested in them because they can tell us things. We're interested in them for what they can tell us about the earth. Being able to pick up a rock and say, oh yeah, that's a granite is one thing, but being able to pick it up and say something about where it cooled, how fast it cooled, was it volcanic, was it underground, etc., etc. That's really the goal of studying rocks. It's not just to be able to know, oh, it's a rock and here's what it is, but rather to be able to know what it can tell us. And I'll kind of talk more about that as we go along. The picture you're looking at is from Iceland. And we'll also talk about what the heck is going on with those rocks. So anyway, okay, so to review a little bit from last time, and if I can get the slide to advance, let's see here. There we go. Remember that we talked about minerals last time. Remember what a mineral is. It is a naturally occurring inorganic solid with a definite chemical composition and a crystal structure. And so a friend of mine, I sent a friend of mine a link to the lecture, and she listened to the first part of it, and then she fell asleep. But no, she listened to the first part of it, and she said, "Okay, but Paul, you mentioned gold and crystal structure," and she said, "I don't think I've ever seen a gold crystal." And I said, well, that's internal, right? That it doesn't matter what the lump of gold looks like. That the internal structure, the internal molecular structure of it would be crystalline in that the atoms would be stacked very, very regularly. But then I got to thinking and I'm like, yeah, but there should be a gold crystal. I mean, there should be a external crystal form. And sure enough, there is. That's what a gold crystal looks like, guys. It's very rare. It doesn't happen very often, but every now and then conditions will allow gold and other precious minerals to grow into crystals like that. So anyway, I just thought I would throw that in there. So if that's a mineral, then what's a rock? Well, we mentioned this last time, and I kind of changed up my definition a little bit just to make it a little more explicit. So remember that a rock is a combination of two or more minerals, which we understand was something like a granite, which is, a little bit of quartz, a little bit of feldspar, some mica, etc., etc. Or it is something that meets all the definitions for a mineral, except it doesn't have a crystal structure, right? And last time we talked about limestone being a great example of that, a rock that actually does have a chemical formula, CaCO3, but it's not crystalline. It's just calcium, carbon, and oxygen all lumped together. So I don't think I'm giving a whole lot away when I, remind you that there's three kinds of rock, right? Igneous, sedimentary, and metamorphic. Today we will be talking about igneous rock. This is rock that forms from molten rock. And we'll talk about sedimentary and metamorphic next time. So let's skip past those for now. And let's think about igneous rocks. So igneous rocks are named or classified based on two things: their composition and their texture. And here's the thing. It doesn't matter how far you go in geology. Igneous rocks always come back to texture and composition. I remember when I was at Florida State taking igneous petrology, which is a whole class in nothing but igneous rocks, and I'm sitting there and, look, I'm a paleontologist. You don't really find fossils in igneous rocks, so they're not really my thing. But I have to take a whole class in this, and so I'm sitting there and I'm trying to learn all these rocks, and igneous rock lab is basically just here's 10 more igneous rocks per week. And so, near the end of the semester, I'm sitting there and I'm just surrounded by these rocks. And I'm just like, oh my gosh, I don't care about any of these rocks. But I'm learning them and I'm looking very discouraged. And the TA pokes her head in and she says, "What's up, Paul?" And I'm like, not an igneous rock guy. And she's like, you having problems? I'm like, I can't keep all this straight. And she said, okay, well, what's the thing that you learned in, Geology 101 about igneous rocks? I'm like, composition and texture. She's like, yep, it is still composition and texture. It always is. So composition, what is the rock made of? And in particular, we're going to track one particular compound. And then texture, how big the mineral grains are, right? When you look at the rock, do you see great big honking of mineral grains sticking out of it? Or like you see on the right in this slide, or when you look at it, is it, just kind of very, very fine grain, and it just looks like lump O igneous rock as you see on the left. Okay, so let's take a closer look at these. What about composition? Well, here's the thing. We're going to track one thing with respect to composition, and that is silica, SiO2. Okay, and if you remember, last time in the mineral lecture, we talked briefly about the silicate minerals, and I showed you that chart, which I should bring up here. I showed you that chart of all of those different silicate structures, and in fact, I really can't help myself. Give me 1 second here, guys. I'm going to bring that chart up. So let me go here. Let's open, and let's open the minerals, and let's go down. This is white. It doesn't have that fancy background that I had last time, but that's okay because here's the chart. So you can see we've got all of these silicate structures here on the right. Okay, so this is what the silicon atom looks like. It's one silicon atom. Let me back up. One silicon atom surrounded by 4 oxygens. This is what we're going to track. How much of this stuff is there in that rock? That's what we care about, because that controls everything else, right? That controls how explosive the volcano is going to be. That controls how quickly the rock is going to break down physically. It also controls how quickly the rock's going to break down chemically. There's all kinds of things associated with that chemical compound silica. And so, when I'm teaching geology, I tell my classes, look, guys, if you can understand silica, that's a lot. That's an awful lot. So that's what we want to track. So we have 3 words that we use: mafic, intermediate, and felsic. Mafic igneous rocks don't have a whole lot of silica. Now, look, in absolute terms, they're still 60-70% silica, right? Because those silicate minerals are the rock forming minerals. When you pick up a rock, odds are it's full of silicate minerals. So, and unless you're in Florida and it's limestone, right? Not silicate. But anyway, so mafic, yeah, low amounts of silica. Intermediate have a little bit more silica, and felsic have even more silica. So the 3 pictures that I have across the bottom there show you what a, let me get my fancy laser pointer thinger going here. Is that the one? Ooh, that's the one. There we go. So the one on the left here is mafic, not a whole lot of silica. The one in the middle is intermediate, and the one on the right is felsic. Now, if you don't know anything and you just look at these photographs, there's a color difference. That color difference is real. Mafic igneous rocks tend to be darker in color, felsic igneous rocks tend to be lighter in color, and intermediate igneous rocks tend to be in between in color. I know I said, and I stand by it, don't use color to identify minerals, but you can use color to identify igneous rocks. It works just fine, okay? At least shade, darker, lighter, etc., etc. So let's take a look. There's a piece of basalt. That is a mafic igneous rock. Here's what it looks like in the wild. This is Hawaii, right? Basalt and mafic igneous rock in general is a very, very common rock. This is what the seafloor is made of. This is what Hawaii is made of. It's what the moon is made of. When a planet forms, a lot of times it's mafic. One way or another. This is the Deccan Traps in India. This is a series of hundreds of lava flows all stacked on top of each other. Every little stripy thing that you see here in this clip is a different lava flow. It also goes on for literally hundreds of square miles, maybe even thousands of square miles. This is a huge volcanic eruption that happened, by the way, about the same time the dinosaurs went extinct. Probably didn't cause it. That extinction is a complicated event, but it surely didn't help at all. So, but yeah, so this is mafic igneous rock. This is an igneous rock flow in Texas. I mean, you don't need to go somewhere spectacular or something like that. This is the Valley of Fire in Texas. I spent a couple days messing around with this lava flow, mapping it and stuff like that. There are, you don't, like I said, this isn't some weird, strange, exotic thing that you need to find. You go out west, you see it everywhere. You just see it everywhere. That picture that I opened with on the rock PowerPoint was a photograph of something called columnar jointing. This is another case of that. This is the Giant's Causeway in Ireland. Legend has it that there was a giant in Ireland. He had a girlfriend across in England, and he wanted to visit her, so he built a road. And yeah, but it's not man-made or person-made or giant-made. It's a completely natural thing. Under certain circumstances, sorry, I got a cough, guys. Under certain circumstances, lava, if allowed to cool properly, will pop into these hexagonal columns that from the top look like a cobblestone road. It really does look like someone fitted those together to make a road. But if we look at it, from the side, and this is also in the Giant's Causeway, you can see that it's not just a surface feature, that it actually goes all the way down. There's a lot of this in Iceland, too. You can find a lot of very dramatic pictures of this columnar jointing. And in fact, if we come back to the United States and we look at the Columbia River basalts, once you know what to look for, you see it, right? There's some columnar joining right there. The lava flow above it didn't do it for some reason, but that one did. And then here's some highly degraded columnar jointing in this flow here. And so, once you learn to look for this, you see it everywhere. It's a very fantasy looking thing. You see it a lot in the background of movies. I think Game of Thrones had some of it in the background at some point. Once you know what to look for, you see it everywhere. But it is very cool. It's very interesting. It's beautiful. I mean, it is just amazing and beautiful, but it is totally natural. And it is something that mafic rock will do given the right conditions. Intermediate rocks aren't quite as common. This is the rock diorite. It's not uncommon. It's not rare or something like that. It's just not quite as common. This is diorite. Diorite gets the award for rock most frequently confused with granite. There are a lot of people out there with, listen to my air quotes, granite countertops who actually have diorite countertops. They can be a little tricky to tell them apart. You look for the quartz. Diorite doesn't have nearly as much quartz as granite does. Quartz is the glassy kind of mineral that you see in granite. The place where you get diorite, which is an intermediate composition volcanic rock, you get a lot of it in volcanoes. This is Mount St. Helens. And so what you have is you have seafloor that is mafic. You have continent that is felsic. Remember when we talked about plate tectonics and I said, well, the continent is basically granite or something like granite. Well, that's felsic. And so as you know, at these convergent plate boundaries where that seafloor goes underneath the continent and melts, as it comes up, it gets more and more and more felsic. And by the time it reaches the surface, a lot of times it's intermediate. And so, you get a lot of intermediate volcanic rock at these ocean continent convergent plate boundaries, where you're mixing felsic rock and mafic rock. So, okay, and then what about felsic rock? Well, everyone's favorite felsic rock, I think, is probably granite. It's pretty common. And if I ask you name a rock, a lot of you are going to say granite, and the ones who don't probably say limestone or something like that. But it's a felsic rock. It has a lot of silica in it. There's what it looks like in the wild. That is Stone Mountain, Georgia, outside of Atlanta, near the town, oddly enough, of Stone Mountain. It is a great big honking piece of granite sticking out of the ground. And you can see here they carved this statue on it. It's a huge statue of, I don't know, Robert E. Lee, Jeb Stuart, I don't know, three treasonous rednecks. So anyway, there's that. Now, as you look at this side of Stone Mountain, you can't really just walk up that, but back around on the other side you can. This is a photo I took the last time I was there. This is near a quarry around the back side, but you can, there's actually a hiking trail that goes up it, and you can hike up the back of it. I am going to try next week to go there. I'm in Charlotte. It's not that far away. If I can either find a place to camp or preferably get a hotel room for the night, I will go down there and I'll do a little video field trip down there for us and show you guys some stuff there. It's really a very interesting place. It is beautiful. That's another picture I took last time I was there. It is beautiful. There's hiking trails all around it, but it is a big honking piece of granite sticking out of the ground. So it's a big piece of felsic igneous rock. Half Dome in Wyoming, which you might know from any number of Ansel Adams photographs, is a big piece of, I believe it's granite, some kind of felsic igneous rock, something like granite, if not exactly granite. But the other thing you want to know about this is all of the rock that you see in this picture is igneous rock. All of this is igneous rock. The Half Dome is not just an isolated thing. It's part of a much larger body of igneous rock, and so it's kind of interesting out there. The granite we've seen so far is kind of whitish. You can also have pink granite. There's two versions of the mineral feldspar. Feldspar is one of the main minerals in granite, and there's two kinds of feldspar. There's a pink feldspar and there's a white feldspar. This is the point in the class when I would be holding up a piece of each, and then I would say, look, if you have the pink feldspar, you make pink granite. If you have the white feldspar, you make white granite. And so so here is the Llano granite. Along the Llano River in Llano, Texas. That's spelled L-L-A-N-O. Two L's make a Y in Spanish. In a region of Texas called the Llano Estacado. So lots of Llanos going on there. It's funny, I've never worked this granite, but I have worked the insects in the river. And so I was out there and snapped some pictures of the granite. The state capitol building in Texas is made of that Llano granite. That granite has pink feldspar in it, and the state capital of Texas is distinctively pink and sparkly when the sun hits it right. The Texas state lawmakers, when they went to build a new capitol, they wanted some rock from Texas, and there needed to be plenty of it, and they didn't want to use the Austin chalk, which is right there, in Austin. So they quarried and built with the Llano granite. Let me go back real quick to the Stone Mountain. There, and let's go to over here. Well, no, that's a prettier picture. The Stone Mountain granite is in buildings all over the South, especially Atlanta. But there are some federal buildings down where y'all are now in Pinellas County that are made of Stone Mountain granite. For a while, the federal government had a contract with this quarrying company to provide them with building stone. And when I go there, I know there's a plaque there that tells about where that granite is. Now, see if I can send you guys to a post office or a VA center or something in Pinellas County that has Stone Mountain granite. So, okay, so that's composition, right? Mafic if it doesn't have a lot of silica, intermediate if it has a bit more silica, and felsic if it has even more silica. So what's the other part? Well, the other part is texture. Now, in the real world, we geologists, we have a whole bunch of different textures, and they have fancier names, aphanetic, phaneritic, porphyritic, and things like that. We're not going to worry about those names, and we're really only going to worry about, right now, a couple of different textures, and we're not going to give them fancy names. We're going to call them fine grained and coarse grained. So fine grained igneous rock. If you look at it, you cannot make out any mineral crystals. Now I know you could squint and maybe there's a little crystal, but no, that doesn't count, right? There's a little one. No, that doesn't count, right? It's mostly mush igneous rock, right? On the other hand, if we look at this granite down here, it is made completely of interlocking grains. It is coarse grained, right? So coarse grained looks like this, made completely of interlocking crystals. Fine grain looks like this, where it basically looks like mush igneous rock. Here's the cool thing. I don't care if you know what the rock is for now, okay? What I care is, what's fun here is that you can pick this rock up without knowing anything else about it. You know it's coarse grained. That means that it cooled slowly, and that slow cooling happens underground. So that rock right there cooled underground, right? This rock here, this rhyolite here, cooled above ground. It cooled more quickly, right? If you cool a rock more slowly, then the elements have time to make themselves into crystals, right? If you cool it quickly, everything's just kind of like done wherever it happens to be sitting, and it really doesn't have time to make nice big crystals. So without knowing the name of an igneous rock, without being able to identify a single crystal in it, if you can just pick it up and know that it cooled underground, that's really something. If you recognize that coarse grain texture, you know it cooled underground. That's just, that's really very powerful thing in the field, right? Because look, here we are back at Stone Mountain. That's granite. And if I was there, I would have an actual piece of the Stone Mountain granite to hold up. So imagine me holding up a piece of granite in front of the classroom, right? That is granite. It is coarse grained. Okay, when you look at it, and when I go out there, I'll take a few pictures of it so you can see it. When you look at it, it's coarse grained. You can make out mineral grains, right? That means it cooled underground. Well, what the heck? That thing is not underground. It's a few hundred feet above ground, right? So what happened, right? Well, now see, this is where we get into the fact that, rocks, we don't just care that, what they're named. We care what they can tell us, right? And so once you realize that that rock cooled underground, now you have a story, okay? This rock is about 300 million years old. And when we do geologic time, I'll talk about how we know that, but for now, just trust me, we do. It's about 300 million years old. So it formed underground about the time, roughly in the time range when Pangea was coming together, right? And so, Asia and Africa, smack into North America, throwing up the Appalachian Mountains. But deep inside the earth, there was enough pressure to melt some rock. And maybe it even rose a little bit up through the crust. Now, if it rose enough, it would breach and be a volcano. We'll talk about those later. Stone Mountain never breached, for reasons we'll also talk about when we talk about volcanoes. So it never reached the surface. So it cooled underground. Well, okay, it's still underground. So what happens next? Well, what happens next is erosion, right? We just threw up a mountain range in what is today the Appalachians. It's much taller than the Himalayas are now. And so those are going to wear away, and they're going to wear away, and they're going to wear away, and they're going to grind down until eventually this piece of granite is exposed. If you've ever been to Stone Mountain, and if you haven't, you should really go. It's very cool, despite the three treasonous rednecks. If you've ever been to Stone Mountain, you know that you hit Stone Mountain granite a long time before you get to actual Stone Mountain. When you look at this, what you're seeing is, the tip of the granite iceberg, so to speak, right? There's a lot more of this granite underground, a lot more. Yeah, so just knowing that's a granite, knowing it cooled underground, leads you down this path to working out the entire story of how that came to be. So that's why geologists are interested in rocks, right? Not just, oh, it's a granite. It's like, well, if this is a granite, then here's a whole sequence of events that had to happen to get this like this. So that's why we worry about it. So once again, composition and texture, right? So both of these rocks are felsic in composition. The granite on the bottom and rhyolite on the top. If I was to melt this rhyolite down and cool it slowly over the course of years, it would make granite. If I was to melt this granite down and cool it quickly, maybe over the course of hours, it would make rhyolite, right? They are chemically the same. The only difference between them is their cooling speed. This one cooled the granite on the bottom, cooled underground and slowly. The rhyolite on the top cooled above ground and quickly, right? And so same thing here, right? These are mafic igneous rocks. This is a piece of gabbro down here on the bottom. It's a little harder to see in gabbro because all the minerals are dark. So it's a little bit harder to see minerals standing out, but you can see them. And so good, thick, big mineral grains all interlocking, gabbro, same chemical composition, but faster cooling, no mineral grains visible anyway. Basalt, right? Same chemical composition, different cooling speed. And so this gives us what I kind of like to call the big six. These are 6 igneous rocks that if you know them, no one is really, no one's going to make fun of you. No one's going to laugh at you for confusing, a granite with some obscure thing like an elasticite or something like that. Or a cyanide or whatever. But so mafic rocks here, intermediate rocks here, and felsic rocks here. And then above the top here, fine grained. And across the bottom here, my computer's locking up in weird ways. Across the bottom, if I can point at it, there we go. Across the bottom, we have coarse grained. And so you combine them, right? Mafic and fine grained is basalt. Mafic and coarse grained is gabbro. Intermediate and fine grained is andesite. Don't be fooled by these little white bits. It's not made of completely interlocking crystals. Andesite's a little bit complicated, but don't be fooled by that. And then intermediate and coarse grained diorite, see how it is completely made of interlocking crystals, okay? And then felsic, granite, if it's coarse grained, and rhyolite if it's fine grained, right? And so you are going to want to know, I'm not going to show you pictures of rocks on the test, or if I do, no, I'm not going to do that because that would just add a level of difficulty to me making the test where I just don't want to go there. If you, sorry, take a breath, Paul. Okay. So what you're going to want to know is, mafic and fine grained is basalt. Mafic and coarse grained is gabbro. Intermediate and fine grained is andesite. Intermediate and coarse grained is diorite. Felsic and fine grained is rhyolite, and felsic and coarse grained is granite, right? You're going to want to know those combinations, and in the notes, I will check and make sure, but I believe there's a chart in the notes showing you that. But pictures are fun too. A couple more random things because they are going to be part of the exercise. Pumice and scoria, right? I've already handed around some pumice when we talked about density, right? And I handed you around that big piece of pumice, and it just wasn't that heavy, right? Both pumice and scoria have air bubbles from gas escaping. Pumice, in the case of pumice, a lot of pumice floats, and you can see that here, this photograph I have of a piece of pumice floating in water. And then scoria won't float, but there it is. Pumice is felsic, scoria is mafic. When you go by lava rock, look at my air quotes on lava rock. Okay, um, you're buying scoria. If you're buying it for landscaping or maybe for your aquarium or something like that. You're buying scoria. That's what that usually is. And so yeah, and then pumice. I don't know. You women, you take pumice to the bathroom with you. That's between you and the rock. I don't want to know anything about that. So anyway, okay. So and then obsidian, kind of everyone's favorite volcanic rock. I think it's volcanic glass. Um, if coarse grained rocks cool slowly over the course of, let's say, years, and fine grained rocks cool quickly over the course of, let's say, minutes, obsidian cools very quickly over the time of, let's say, seconds, right? And for this to happen, what needs to happen is that rock needs to do what you see in that picture on the right, right? It needs to be flowing into the water, right? You need water to quench that rock. Fine grained rocks do have crystals in them. You just need a microscope to see them. Obsidian doesn't have any crystals. I don't care what kind of microscope you put that thing under. There's no crystals. Okay, it's just chemicals frozen in place. It has that really interesting conchoidal fracture that lets you make blades out of it. You can make, spear points and arrowheads and things like that. It can make a very, very sharp cutting tool. It really is just amazing. And then there's one other thing I wanted to show you, and that is a rock called a porphyry. So let's think about this. Let's imagine a volcano, and so you're a body of magma underneath the earth, underneath that volcano, and you're hanging out down there, and you're cooling slowly. You're making big crystals. Life is good. You're like, hey, 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 I'm going to be a granite and somebody's going to put me and make me into their countertop or something like that. It's going to be awesome. And here we go. And I just got a little bit of liquid left to cool and everything's good. And then the volcano erupts, right? So now you are running over the ground. You're no longer insulated underground. And so what's going to happen? That remaining liquid is going to cool quickly, like right away. Okay, you just made a rock called a porphyry. Now, there's a lot of different kinds. We're not going to worry about that. We're just going to call it a porphyry. And the trick with porphyries is they have two different sizes of crystal that relate to two different cooling speeds, right? If I look at this rock here, I've got these larger crystals here that formed when the rock was cooling slowly. And then I've got all of this crystal, or not crystal, but all this matrix around it, all of this mush that was liquid, and then when the volcano erupted, it solidified into fine-grained igneous rock. So I've got two different cooling speeds here. So, and so we call that a porphyry. In the real world, we would name it an andesite porphyry or a dacite porphyry or whatever porphyry or rhyolite porphyry. We're not going to worry about that. If you see those two different crystal sizes like that, it's a porphyry. Okay, so that's igneous rocks. And let me get out of the PowerPoint. One more thing. Sorry, see? This is what happens when I don't know what's coming. Remember that, and I'm just going to leave it like this, but remember that the thing that we learn, actually, that's a really cool picture. Let's make it bigger. Remember that the thing that we learn from igneous rocks is we learn the thermal history of the rock, right? We learn where it cooled, how quickly it cooled, things like that, right? Rocks from really, really deep can provide us insight into the chemistry of the Earth's interior. There are igneous rocks that come straight up from the mantle. And when you find one of those, now chemically, you have a window into what the mantle is composed of. And so it's a very, very valuable thing. So igneous petrologists are like physical chemists. If you're a person who likes chemistry, you would love igneous petrology. So let's take a look at the exercise. Let's see, actually, the exercise here. So here's the exercise. What did I just do? I just closed the exercise. I'm sorry, guys. Oh heck, I gotta download it from my courses. Bear with me, guys. I might edit this out. This might be my first chance to try editing in Camtasia. So let's go to my, oh, I'll show you where the exercise is. Okay, that's cool. So I'm going to show you where the exercise is. I'm going to pretend I planned this the whole time. Everything on the internet is running really slow because everyone is streaming all the things now. So let's see, here we go. One of my Earth Science sections, and we go into course content. And if we look here in lab exercises, and right now Igneous Rocks is hidden from you. When I finish this lecture, I will unlock it, unhide it so that you guys can see it. And so now if I hit download and I hit just open it, don't actually download it. That's why I couldn't open it before, because I opened it from here. And we'll give it a couple seconds to do this. So how you doing, guys? Washing your hands, not touching your face. Try not to go out. Try not to be too close to people. All that good stuff. And we should almost be there. There we go. And come on, Word. Come on, Word. Open the file. There we go. Sorry about that, guys. So anyway, so you can see we've got some pictures and we got some descriptions. And so you're going to use those pictures and descriptions, honestly, mostly the descriptions, to identify the rock. This is, as I'm looking down through these, I'm like, I'm pretty sure I showed you all those pictures in the course of that lecture, but that's okay. And so what you want to do then is use the Excel spreadsheet, which I will try really hard to not close on you, to identify the rock. Now, so this is in the same part of my courses as the document was. It's right there. It will not work if you just open it in my courses. The formatting is all wonky. Okay, so don't do that. You want to actually download it and open it using Excel. As an SPC student, you can download Excel. If you haven't done that, you should probably do that. But anyway, and so what you get is this. Now there's 3 tabs down here: igneous, sedimentary, and metamorphic. You obviously, for the igneous rocks, want igneous. Okay, and so now the chart looks like a little bit of a train wreck at first, but it's not that bad. So first of all, let's just look at this side of the chart right here. So composition and texture, right? Now here are the big 6 down here that we talked about, right? Mafic and fine-grained is basalt. Mafic and coarse-grained is gabbro. The rock names are underlined, okay? Intermediate and fine-grained is andesite. Intermediate and coarse-grained is diorite. And then felsic and fine-grained is rhyolite. Felsic and coarse-grained is granite. Okay, so there's the big 6 there. And then glassy texture is obsidian. Notice I put obsidian across all 3 compositions. That's because you don't know what obsidian's composition is. I know it's dark, which would make you think it's mafic, but it's not. Okay, you don't know obsidian's composition unless you put it in something like an X-ray diffractometer, and we don't have those, at least not here. So anyway, and then we've got those 2 vesicular rocks. Vesicular is a fancy word for the rock has bubbles in it. If it's dark, it's scoria. If it's light, it's pumice. Okay, we don't really have any intermediate vesicular rocks. And then on the left side here, you can see that I put porphyry across all these textures because it kind of has all those textures in it. And so remember, that's the one that's a combination of fine grain and coarse grain. We also don't worry about composition for these porphyritic rocks, at least not in this class. We don't. So anyway, so I've kind of got a little how to use the chart down here. So which gives you kind of a series of steps that you can go through. I won't go through them. You can read as easily as I can. And so there they are. So what you want to do is use this description and maybe the picture a little bit, but really mostly the description to give the rock a name, right? Give the rock a name, put, save this document, put it in the Dropbox when you're done. Bingo, you're done with igneous rocks. There's not that many of them, and there is one per on the chart. So once you like I'm saying, there's not two granites, okay? And I'm pretty sure 6, 7, 8, 9, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Yeah, so there's 9 rocks over here on the chart. There's 9 rocks in the Word document, so there'll be one per. So once you get one done, if you want to cross it off, cross it off. That'll narrow down the choices for you. Okay. Alrighty, I believe that's everything you need to know. And so yes, I'm going to go ahead and stop this, and y'all watch it. And by the time you're watching it, everything will be unlocked, and you'll be able to do that. Okay, y'all, take care. Bye bye.